Hello everyone. In the last video for this spring semester, we're going to talk about multistage hydraulic fracturing. I just see that there is a typo over there. Okay, in multistage hydraulic fracturing, the purpose is to increase surface area with multiple fractures. If you remember what we did at the very beginning of this course and this series of videos, is that we found out that hydraulic fractures will propagate always perpendicular to the least principal stress. In cases where the least principal stress is horizontal, that will result in vertical fractures. For example, in this case of the Permian Basin, we know that the minimum principal stress is oriented more or less north-south, and as a result, the fractures in the Permian Basin, they tend to be vertical fractures that grow in direction east-west. And if we look at that in 3 dimensions, this is going to look something like this, where the fractures are planes, which are perpendicular to the minimum principal stress, which in this case is horizontal. They tend to grow up and down and east and west. Now, the objective of increasing the surface of the fractures is related also to the direction in which we might drill a horizontal wellbore. Preferentially, we want these fractures to be perpendicular to the wellbore, because in that way we are maximizing the surface area possible to make out of this vertical wellbore. If we were in this example in the Permian Basin to drill a wellbore in direction east-west, our fracture will still grow in direction east-west. So if we have multiple stages, at some point they will link up and they will just make a large hydraulic fracture, which is going to have a large surface, but not as large as the one with fractures perpendicular to the least principal stress and also perpendicular in this case to the direction of the wellbore. So each stage ideally should have its own fracture, one or more. And you see a very similar schematic over here of the situation that we have on the right. Well, now let's try to put some dimensions to this new fracture geometry when we have several fractures out of a horizontal wellbore. And for that, we're going to define some new parameters that are important for fracture design. Before, we already saw what was the fracture half length, what is the fracture height, and what is the fracture width, which is not drawn in this schematic. Well, now we're going to add to these design dimensions the spacing between the fractures and also the length of the wellbore. With all of these parameters, ideally, if we assume that all these fractures are planar and we have one fracture out of each stage, we could compute what is the surface area for such multi-stage hydraulic fracture treatment. For example, if we have a vertical wellbore only, without a fracture, the area of such wellbore encased in contact with the reservoir will be in the order of 300 square feet, which is more or less the size of a room. If we had one fracture grown out of a vertical wellbore, we will have a much larger area with compared to the vertical wellbore. Here, just to complete this example, I have assumed that the fracture height is 100 feet and the radius of the wellbore is half a foot. The length of the laterals and horizontals is 5,000 feet. the fracture half length is 500 feet, and last, the spacing between the fractures is 50 feet. Okay, so with all these numbers, we can compute the numbers I'm mentioning over here. Again, if we have just a vertical wellbore, the area of the rock in contact with the wellbore, which is draining into the wellbore, is going to be about the area of a room. If we have a single hydraulic fracture, that's going to be much bigger. And here I approximated that to the area of more or less 3.5 football fields. So you can have a better idea about how much we have increased now our surface area in contact with the reservoir, which is going to produce larger flow rates. But now if we have multiple fractures, we have a much larger area, in this case 100 times larger because we have 100 fractures, and now we have an area equivalent to about 350 football fields, which is quite large. And this is the main advantage of these wellbores, that you just drill one wellbore, you extend the lateral, and you get a much higher specific surface and in general surface of the wellbore in contact with the reservoir. Okay, so now that we have gone through this example, there is one more possible extension to this geometry. Now we could repeat these multiple stages out of a horizontal wellbore for several wellbores drilled out of a single path here on the surface. And here you have an image that exemplifies that, in which we have a path on the surface, like this one. We have wellbores that go down into the subsurface, and they extend in different directions, covering the entire reservoir area. Something very important, and we're going to get back to this later on, to consider into unconventionals where we want to practice hydraulic fracturing, is that the amount of, or let me tell you, the size of the reservoir, it depends on the size of the stimulated volume or the size of the region that you hydraulically fracture. It's not related directly to the available hydrocarbon in situ, but more to the area that you can fracture or the volume that you can fracture. So now, if we want to increase this volume, we can have several wellbores where we're going to have one more parameter to design this wellbore, which is the spacing between the wellbores. So we before added the length of the lateral, now we can also add the spacing between the wellbores. And you could already imagine that managing and setting all of these variables, these new variables like the spacing between stages from here to there, the length of the lateral, the spacing between the wellbores, that's going to be something very important because is what is going to affect what is the cost of the treatment, but it's also going to affect what is the resulting production. So from the point of view of economics, these hydraulic fracturing geometric parameters are going to be quite important. And for example, if we were to plot what is the cost of the treatment for a single hydraulic fracturing job, just for a single wellbore, then, and we plot this as function of the number of fractures, we would very likely see in most cases that the cost of the treatment is going to have some initial value, and then as you increase the number of fractures and you decrease the spacing between the fractures, this cost is going to increase as you increase the number of fractures and decrease the spacing, because you need more fluids to to put into the fractures and more time to do those fractures, so that cost is going to increase quite quickly as soon as you hit a critical value. On the other hand, we know that the production revenue is also going to depend on the number of fractures. And for if you have a few fractures, probably that's not going to be enough to pay for the actually it's going to have a negative value on your project. But if you increase your number of fractures, this is going to the production is going to increase. But at some point, if you keep on decreasing the spacing, probably you're not going to drain effectively the reservoir anymore, and this is going to hit a sort of a plateau. So putting all these things together is very important, and all of this is going to depend, as we were saying before, on the spacing between the fractures, the length of the lateral, and the spacing between wellbores as well. Okay, so let's talk first about the spacing between the fractures. If you place hydraulic fractures too close to each other, they are going to interfere. And what I mean with interfere is that mechanically they are going to feel each other. Once you play a fracture, the next fracture is going to feel the presence of the previous one. And something that is going to happen, it's similar to what I'm going to draw right now. If we have a horizontal wellbore in which this is the toe of the wellbore, that means the point with the highest measured depth, and let's say that at some point we isolate this region, and we have here in stage, we create a fracture. Let's assume this fracture is more or less plane, and after where we're fracturing, we inject propant, so it's filled with propant. The rock that is right next to the fracture is going to have a stress which is not the same as the stress which it had before. So if we isolate a piece of rock near this fracture, in the direction perpendicular to the fracture, which is the direction in this case of the minimum principal stress, we're going to have an additional stress caused by the presence of the fracture. This is something which is called stress shadow. And here in this schematic, we can see that these stresses in the direction XX, which is the one I'm referring right now, the blue curve, and also in direction YY, which in this case is the one in pink, those two are going to increase as you get closer to the fracture, and it's going to depend also on some other variables like the height of the fracture as well. But in summary, once you place a fracture and you prop it, this is going to create a stress around the fracture, which is going to alter the in situ state of stress. And as a result, when I go into the next stage after it's plugged and I do a perforation, the next fracture might feel the presence of the previous fracture if you put it too close, and that could cause the new fracture to grow away from the previous fracture. And this effect is usually called a stress shadow. And the meaning is that if you cannot place the fractures too close, because if you place them too close, they are going to interact with each other. Actually, if you were to continue with this same spacing and you wanted to place a new fracture, sometimes the change of stress imparted by the proximity of new fractures could be so large that you could have something which is called a stress reversal, in which your minimum principal stress is not in the direction in which it was before. Like for example here, let's add a coordinate system. Let's say that, let me change this. Let's say this is the north and this is the east. If your minimum principal stress before was in direction east-west, like in this case, if you change the stresses locally so that the new minimum principal stress gets larger in direction east-west than in direction north-south, probably at this point now, the new local minimum principal stress could be this one. And as a result, your hydraulic fracture might grow perpendicular to that one and might hit the previous one. These fracture interferences are not ideal and generally are not good for hydraulic fracturing, because now your fracture is not extending over the reservoir, but it's rather sometimes going very close to the wellbore and hitting previous fractures. So we want to optimize the spacing between these hydraulic fractures so that that doesn't happen. And that's going to depend on several variables, as we were saying before. And here I have summarized that into one equation. The spacing between the fractures should be proportional to the net pressure that you use for a hydraulic treatment, and that is also going to be related to the difference in principal stresses. In order to avoid this reversal between the intermediate principal stress S2 and the least principal stress S3, if this value is too large, you can use a large net pressure and there is not going to be any problem. There is not going to be any reversal because the change of stress is going to be relatively small compared to the amount needed to cause that reversal. So the amount needed to cause a reversal of the state of stress is S2 minus S3. So the larger this value, the further away you're going to be from this reversal. The closer you are to S2 is to S3, that means that let's say that we are in normal faulting, that would mean that SH max is similar to SH mean. In that case, if you change a little bit the stress in your formation, then your new stress, it could be either in the direction of SH mean, or now it could turn to the old direction of SH max. So the fracture doesn't know where to go. The stresses change locally, and you have something like you see over here. And this is also going to be proportional to the height of the fracture. The bigger the height of the fracture, the longer this stress shadow extends into the formation. I have one example to show over here about the importance of the difference between stresses S2 and S3. And this is given in this paper over here that shows and quantifies for the state of Texas what is the difference between the minimum principal stress and the maximum principal stress. I'm trying to zoom in. I don't know why it doesn't work. Let me try again. Probably I'll just download this file. Let me try one more time. No, doesn't want to. Okay. Okay, here we go. This is the paper, and this is the image that I wanted to share with you. Here we have the state of Texas, and this parameter quantifies the state of stress going from normal faulting to reverse faulting, but also quantifies the difference between horizontal stresses. For example, in this case, for radial normal faulting, this referred to cases in which the difference between SH min and SH max is equal to 0. In this case, for this parameter A5 equal to 0. As you can see, in the state of Texas, that happens in a few locations, like close here to the Barnett Shale. In some places close to the Barnett Shale, the difference between SH max and SH min is relatively small. And in those places, you could have these instances that we were saying of stress reversal because of the presence of a hydraulic fracture. However, if we go to a case like, for example, in here near the region of the Permian Basin in Snyder, we see that the state of stress approximates something more closely related to strike slip, in which the difference between SH min and SH max is quite large. And actually, for that case, there is an example over here of more circles. Let's see if the other version looks a little bit better. And for those more circles that we see over here, the value of this is the minimum horizontal stress, and you can see this quite smaller than the maximum horizontal stress and the vertical effective stress. So in cases here, the difference is about more than 6 megapascals, when the difference between the least principal stress here, sigma 3, and sigma 2 is large, then the effects of the interference between the wellbores and the interference between fractures is going to be less. So we can place these fractures closer to each other. Okay, so let me summarize what I've said in writing. And we already have that equation over there. I'm going to add here that if the net pressure that you use for a hydraulic fracture treatment is smaller than the difference between S2 and S3, then very likely you're not going to have fracture interaction, and your fractures are going to grow more or less planar without bending. However, if your net pressure, which is, if it is larger than the difference between these stresses, then probably you're going to have fracture interaction. The net pressure for typical hydraulic fracture completions varies from place to place, but is usually in the order of a few hundred psi. And you could compare that with the typical differences between the intermediate and least principal stress, and that can give you an idea for places in which you should be worried about the spacing between the fractures. And I hope that also you remember from our previous discussion that sometimes also when the net pressure is higher than the difference between S3 and let's just be here a little bit more concise and a little bit more accurate with this. When this is higher than the difference between vertical stress and the minimum principal stress, in these cases is when you can get also into T-shaped fractures, because your total pressure could be higher than the vertical stress, and so you could grow fractures which are horizontal. All right. Let's see how can you avert these problems of fracture interferences. There are many cases or many ways to try to get rid of these effects. For example, here, if you were to set some spacing, as we were saying before, and you keep lowering down, your fractures may start to hit into each other, which is not ideal. So one way to decrease these effects is to do something which is called superfracturing. In this modality of fracturing, what you can do is, instead of placing fractures immediately one to each other, you can start by doing one fracture, for example, here, number 1 and 1 prime in different wellbores, and instead of placing one immediately after, you place another one in another wellbore, but only after placing a second fracture further away, in this case, in wellbores number 1 and 3. Why do you do that? Because once you create one, you create a stress shadow. Same here. When you create 2, you create also a stress shadow. Same over here. But those two stress shadows may cancel out, so that your fracture that is growing out of wellbore number 2, it may grow straight. And the same case for the lower wellbore. And you can repeat that, so that before placing a fracture into a region which has a stress, let's say an unbalanced stress shadow, you just place it only after having those stress shadow effects cancelled, so your fracture may grow straight. This is what is called zipper fracturing. Another alternative for getting rid of some of these effects of fracture interaction is to use what is called a wine rack pattern, in which if you have a formation which is thick enough, I'm doing here a 3D schematic, you could have wellbores that come into this formation, and let's say I have this schematic comes out more or less okay. You have a wellbore over here, you have another wellbore over here, another one over there, and you can combine the zipper fracturing with the wine rack fracturing. So here we're going to make one fracture on the plane of this formation, and then we're going to have another wellbore that on the plane of this cross section we have another wellbore at a lower location, but this one extends outside the plane. Let me do the same over here, and in there you have now a new fracture that grows a little bit further from the previous position, right? So here there is a distance which is a little bit further away from this plane. So in this way, because you see this looks like a W, and also looks like a wine rack pattern, you can also maximize, in this case, the volume that you are stimulating without having too much interference. And here we have added one new fracture design variable to our completion, which is the vertical distance between the wellbores. Remember that before we had the distance between the wellbores, and now we have also this one was a horizontal distance between the wellbores. Now we have a vertical distance between wellbores. Something else that you may want to optimize your hydraulic fracture treatment. All right, let's see what's next. So far we have discussed the application for doing hydraulic fracture treatment out of a stage after plugging and just with one perforation. This used to be done long time ago, but now what is much more popular and much more effective is that for the same uh, pressurized section or plug section to have multiple stages and multiple perforations in each section. So here we're going to have multiple clusters of perforations, and we're going to see what is the benefit of that right now. And this will be more or less the schematic valid for this new case. Now we have a horizontal wellbore. We have plugged the sections of this horizontal wellbore, and in this section of the horizontal wellbore, or in each stage, this will be one stage, we have several clusters. In this case, we have 1, 2, 3, 4, 5 clusters. That number can depend on the hydraulic fracture design. And when you do the hydraulic fracturing, you're injecting simultaneously a hydraulic fracturing fluid and after propant in all these clusters at the same time. The advantage of this type of completion, in which you're creating multiple fractures at the same time, is that you do not worry that much about setting a specific spacing between the fractures, but you just rather let the system to equilibrate on its own. Sometimes you can have fractures that grow quite nicely out of all of the clusters, which is not commonly the case. It's rather the exception, but it might happen. But in some other cases, you might have some clusters that they have very short fractures or no fractures at all. But the advantage of this approach is that even though you may be doing a few more clusters for each stage, you are letting those fractures to propagate as they want and trying to optimize these stress shadows and interferences so that those cancel each other, and the fractures that can grow, they grow. The fractures that they cannot grow, they just can't. In some way, I like to call this type of fracturing, it is the survival of the fittest, because really the fractures that can grow, they are going to grow, and the ones that cannot, they are just going to stay small, or they will never propagate. And in this case, also it's very important that there are, as we were saying before, some advantages and disadvantages of this approach. Let me summarize those here on the right. This is going to be multi-cluster completion, and among the advantages of this approach, we could say that we can have more surface area, because, for example, you could set based on your studies in a fracture spacing which is actually too long, and something much smaller is the reality. And if you go with that fracture spacing which is too long, you might be losing quite a bit of surface area. You could also mitigate the effects of fracture interaction, because basically now you're just letting the fractures to grow on their own without trying to push, for example, a fracture to grow next to another fracture, which is creating quite a bit of stress shadow. And it's also faster operationally, because you can do many fractures at the same time. Some disadvantages, however, are that you can have uneven proppant placing, and that's not good because you could make some of these fractures to propagate, but they might not get enough propant. Actually, if we, in this case, are injecting here from left to right, it's likely that most of the propant is going to go into the first fracture, and little propant is going to get into other fractures, the ones that are further away from the first fracture. So that uneven propant placing is also going to result in fractures that are not very conductive over time. Here I have also summarized typical parameters that have been used for hydraulic fracturing in recent years for the Permian Basin. The length of the laterals, they are usually larger than 10,000 feet. The number of stages, each of these from here to there, it varies, but it can be 40 stages or even more. The number of clusters in each stage, it's also a variable, but usually goes from 4 to 15 perforation clusters per each stage. Usually you have 6 perforations every linear foot of wellbore, and they are offset at angles of 60 degrees in each of those clusters. And the injection rates, they go from around 2 barrels per minute per perforation. And you can also measure that in terms of the linear foot of the wellbore, and that also can be in the order of 60 barrels per linear foot of horizontal wellbore. And the propant, properly, for the propant, it's nice to try to have an idea about what that means. 2,000 pounds per linear foot, that it's more or less the weight of a car in propant per every linear foot of the wellbore. If you multiply that times 10,000 feet, you can imagine that here we are using quite a bit of propant and also quite a bit of fluid, in this case 60 barrels per linear foot for this hydraulic fracture completion. So this hydraulic fracture completion, it's very intensive in the use of water and propant. So that's why some of the latest advances in hydraulic fracture try to reduce these quantities. Okay, we have got more or less to the end of the hydraulic fracture design, especially for the geometrical properties involved in the design. And so far we have assumed mostly planar fractures in which the fracture is perpendicular to the minimum principal stress, and there is just one fracture out of each cluster or each stage if we just have one perforation cluster per stage. Well, this conceptual image that we have of planar fractures, and let me come back to some of the first images that I showed here, like this one, it appears that we have some field data that it is not very much the case. This conceptual idea is not a reality. Some other conceptual ideas about fracturing are closer to what you see in this image, with multiple branches almost looking like fractal structures out of a wellbore, and those aren't also quite real either. And although either we have more fractures that look like planes or something that is more ramified, it really depends on the hydraulic fracture treatment and on the particular formation that is being fractured. And thanks to new investigations, now we have a better idea about how hydraulic fractures really look in the subsurface. The first tool that has, the first tool I'm going to mention that has helped us to get a better idea about how hydraulic fractures look in the subsurface is microseismicity. Microseismicity is the use of geophones in order to locate how the rock breaks in the subsurface. And we can place these geophones either in adjacent wellbores or in surface, and by tracking how the rock breaks in the subsurface, we could say more or less where the fracture is going. This is, imagine a case, and this actually happened to me in my house, in which in the fall there were many dry leaves outside, and there was an animal outside that was walking around. I think it was a weasel. I couldn't see the weasel, but I heard the noise of the dry leaves breaking and the branches breaking that told me that the weasel was probably going next to my bedroom, but I didn't see it. In this case, it's very similar. With microseismicity, we don't actually see where the hydraulic fracture is, but we see what hydraulic fracture is doing and how it's breaking the rock around the hydraulic fracture. All right, so operationally, as I was saying, we mount these geophones either in wellbores or in the surface, so we see how the fractures occur in the subsurface. This is very similar to the triangulation of earthquakes. It's exactly the same, but just at a smaller scale. And what we get as a result are the locations of the events of rock failure. And these are the dots that you see over here. Each of these dots results from the triangulation of the waves, elastic waves going every time a fracture happens and the rock breaks. The waves travel to the geophones and tell us where the rock is breaking. And let me show one other example over here. That is going to be, actually, by the way, this article is fantastic. You will find it. You will find a link in the homework problems. But let me just go right now to that so you can see it. If you click on this link, you're going to find this article, which is free to everyone and has a very nice discussion and introduction to microseismicity that is going to tell us, I'm just looking for a good image to show the final result, and this is a good one. It's going to tell us where the rock is breaking next to the hydraulic fracture. Again, it doesn't tell us where exactly the hydraulic fracture is, what is its shape, but it's already telling us how the rock is breaking around the fractures. And by looking at these clouds of events, we can locate where the hydraulic fracture is going. For example, in this case, each color corresponds to a different stage. So for example, we can actually see that stage number 1, which is closer to the toe of the wellbore, it's the one which is over here. That means a hydraulic fracture broke the rock in this location. Stage number 2, adjacent to this, is this one, and 3 and 4 and so over. So with the help of induced seismicity, with the help of microseismicity, we can more or less tell where the fractures are happening. And here, let me come back to my notes. The interpretation of this is very simply put into an ideal model, is that we have one main hydraulic fracture, sometimes can be more than one. We're going to see just that in a bit, out of which we have ramifications or reactivations of fractures near these main hydraulic fractures. But these are not any type of fractures. Actually, what produces most of the microseismicity are rock are events of the rock failing in shear. So each of these events, each of these dots, is actually an event of shear failure in the rock. And we could, if we were to analyze that, this should, let me zoom out of this, this would be interpreted as rock surfaces just failing in shear with respect to each other. That's what is causing the waves to propagate and go to the geophones. Once we do the triangulation, we actually locate, we can locate where that is coming from. And as we were saying, this is a reactivation in shear, which means that in terms of the Morse circle, our effective stresses are going from a state in which they are stable to a state in which they are touching the shear failure line. And this is very similar to what we saw in the case of a fault reactivation, but at a much smaller scale. These are very small events. Usually the microseismicity in the field for hydraulic fracturing is in the order of in the Richter scale in negative numbers, -3, -2, -1, sometimes up to 0. And that's why it's called micro, because it is quite small. And usually, just to give you an idea, this type of events of an event of a magnitude 3, -3. Let me repeat that because it's very important. An event of a magnitude in the Richter scale m equal to -3, that is caused more or less by the failure of a surface reactivation in shear, or more or less 1 meter square. So we're talking about very small sizes here of reactivation. Okay, so if we have, again, several fractures, these clouds are going to tell us the reach of the hydraulic fracture and the reach of the change in pore pressure near the fracture that is causing such reactivation in shear. Sometimes, unintentionally, we could run also into a fault. If you were to inject fluids near a fault and decrease the pore pressure, you could also reactivate a fault. And that's something that is not going to result in microseismicity, but is going to result in a seismicity which has a magnitude which is larger than 0, and that's something that we do not want to do. So ideally, you would like to map the faults, like for example, here in this figure, these are 3 lateral wellbores, and these are mapped faults here, there, and there, that we want to stay away from them, because actually if we were to increase the pore pressure, we might reactivate them. And this is actually what you see in this example, that many of the bends in this place align with this fault. And that's something that, as I was saying before, that's something that we do not want to do. So that's why it's very important to map faults near the places where hydraulic fracturing is performed. All right, so with all this microseismicity, we can have a better idea about the stimulated volume by the hydraulic fractures. Actually, thanks to this reactivation of fractures in shear, if these shear fractures are conductive, they are going to also help to the flow of fluids from the rock matrix into these small fractures and then into the big fracture, and that's going to help production. Actually, these smaller fractures are going to even are going to increase even further the surface of the rock or the reservoir in contact with the wellbore and help to increase the production rates. There is one study of Dr. Patzek that says that doing analysis of production from the Barnett Shale, if you do a back calculation of what is the spacing between fractures that is required so that you achieve the production rates that are observed in the field, combining that with the permeability of shales, which is in the order of nanodarcies, the spacing between fractures is in the order of 1 meter, which means that in many of these cases, we have a much higher surface area than the one that we computed before with just the hydraulic fractures. And one of the reasons for that is that we have reactivation of shear fractures, and those reactivated shear fractures are contributing again to the production of fluids. So now, if we account for all of these reactivated shear fractures, we can compute something which is called an estimated reservoir volume. And our production and estimated ultimate recovery is going to be proportional to this estimated reservoir volume. As we were saying before, in unconventionals, you could have a super large reservoir, but if you don't stimulate it, you're not going to get any production in economic terms. If you just were to drill a vertical wellbore, then your flow rate is going to be very small. In order to actually produce it with economic rates, you need to do hydraulic fracturing, and therefore your estimated ultimate recovery is going to depend on this estimated reservoir volume. Just to make a very small simplification here, something very simple, we can calculate this estimated reservoir volume by multiplying the recovery factor, which in shales is in the order of 10% or less for oil. For gas is a little bit larger, times the estimated reservoir volume, times the porosity of the rock, times 1 minus water saturation, and that divided the volume factor, and that's going to give us the estimated ultimate recovery. In conventionals, for example, instead of utilizing the stimulated reservoir volume, you use the total volume of the reservoir. Well, in unconventional, it's not like that. You use the stimulated reservoir volume because that's what you can economically produce. And one more thing that I'd like to add about the stimulated reservoir volume is that having a large stimulated reservoir volume in general, it's something desirable, but sometimes it's not everything. And what I mean here is that if we were to plot a stimulated reservoir volume and here cumulative production for a given hydraulic fracture treatment, what you might expect from our previous discussion is that the bigger the stimulated reservoir volume, the larger your production is going to be. And that kind of makes sense, and it's along the lines of what we were discussing before. And for some formations, that could be the case. However, there are some cases in which you can have a very large stimulated reservoir volume, but very little production. The reason for that is that you could have done a very good fracturing job, but some of your fractures are not propped. So here you have unpropped fractures. A solution to overcome this problem is to use proppants which are quite small. Actually, nowadays the industry is going into a trend of using what I'll call micro proppants, so they can get not only into big fractures like this big hydraulic fracture over here, but they can also get into smaller fractures, like some of the reactive fractures like the one shown over here, and some others type of segmented fractures I'm going to discuss in just a minute. And another way is to use also acids. Acids can etch the surfaces of fractures, and that can help to increase conductivity even if you don't have propan in them. And there are also some other cases in which you have a very small reservoir volume, but you have um, a large production. In this case, that is also feasible, and sometimes this is associated with what is called aseismic slip. And that refers to cases in which when you have this type of shear failure of surfaces that doesn't produce enough seismicity, and you cannot hear it, you cannot measure it with geophones. You can have fractures that are failing in the subsurface, but you cannot measure it. But anyways, those are contributing to fluid flow. So in these cases, you might have a large cumulative production, even though your SRV is relatively small. And the last thing we're going to see about multi-stage hydraulic fracturing is the case of what is called fracture segmentation. This first hypothesis that we put together in order to explain fracture complexity, let's put a number here. The first one was reactivations of fracture in shear. And let me put this over here, number one, reactivation of fractures in shear. And fracture segmentation, they both help explain the complexity of hydraulic fracture, and they are not a single plane. And let me go in detail about what fracture segmentation is. If you remember from previous discussions, we said that if we have a hydraulic fracture which is propagating as a single plane, as we have been doing before in our analysis, if we have instances in which we have a change of stress and the tip of the fracture encounters this change of stress, in this case in the form of out of plane shear, this is going to cause the fracture to segment. And this fracture is going to turn and is going to adjust into a new orientation of propagation that for this particular case is going to be several planes of propagation, and that's what is called fracture segmentation. And let me show an example of this case. Here we have an image of an outcrop, and this is a joint. It's not a fluid-driven fracture, but it's anyways an open bone fracture in which we have a propagation of a fracture in this layer, and as you go to the next layer, the fracture splits into several planes because in the layer underneath, the direction of the state of stress is not the same. So in this case, on the top, the minimum principal stress was perpendicular to the plane of the fracture, but because of changes in tectonic strains or in properties of the rock in the layer underneath, now the direction of the principal stress is not anymore the direction in the previous layer, and that's why we have this phenomenon which is called segmentation, and which this produces is actually many fractures that that go out of a single fracture. and this is the phenomenon of segmentation. And we have also seen that in wellbores in the field. And here you have one example. This is a very nice paper. Let me go to the title so you can see which one I mean. It's a paper that publishes the results of sampling wellbores that have been hydraulically fractured. And here you can see the SPE number. This was done in the Permian, and the objective was, as I was saying before, to do hydraulic fracturing and after to retrieve cores out of that region hydraulically fractured. And one of the main findings of this study, here we see also events of microseismicity, is that the investigators that did this, they found multiple fractures in regions that were actually quite close to each other. Here you can see these are hydraulic fractures which are spaced at less than 1 foot. And here you have an image of a wellbore that shows the presence of multiple hydraulic fractures. In this case, you have more or less 20 fractures in about 20 feet. What is showing that many of these hydraulic fractures actually they propagate in clusters rather than in a single fracture. If we were to put this together into a schematic, this will look something like this. Let me change the color. If we have a horizontal wellbore, and let's say that we have here 3 clusters with perforations, what the images and the study on the left show is that many of these hydraulic fractures appear to look more like clusters of fractures propagating out of these also clusters of perforations. Many of them, they align with the expected direction of the hydraulic fracture, but they show that we do not have such planar and, let's say, planar and thick hydraulic fractures as we thought before, but they are actually thinner and you have a larger number. And in addition to that, we will have some of the previous also fractures reactivated in shear close to these formations and close to these main fractures. So in green, we have the fractures reactivated in shear. In red, we have the fractures which are in mode 1 and also mode 1-3, which are the reactivated, which are the segmented fractures. And just to tell you the case, and which I think is the truth in the current advance of hydraulic fracturing, what you actually have in the subsurface is going to depend on specific cases, and it's going to depend also on the hydraulic fracture treatment, the fluid injection parameters, and all of that. And there are still studies trying to understand what really goes on in the subsurface, and so far no one really knows what is actually happening in every single place in which you do hydraulic fracturing. But to my view, what you see over here is what is something which is compatible to many cases that have been done in the field. This will be the green, as we said, are the shear fractures, and the red will be hydraulic fractures. hydraulic, and here I'm putting together mode 1 and mode 1 and mode 3. Mode 1 plus mode 3. This will be the segmented fractures. All right, with this we end the chapter on hydraulic fracture, and I hope you enjoyed this video and you enjoyed all the videos. Just to close the lectures for the semester, in general, I really hope that you enjoy this class, and also keep tuned to my channel, because I'm going to continue uploading some videos over the summer related to topics of geomechanics. There's going to be one more video associated with today's lecture, and that is about the homework.